Consider this question for a moment. What exactly are minerals? Are they living? Can they be man-made? Can you give a definition? Scientists define a mineral as a naturally occurring, inorganic compound with a definite composition and structure. Complicated? Not really, once we break this definition down to show what all minerals have in common. For instance, consider this. Are these substances minerals? The plastic that this bottle is made of? Or the concrete that makes this building possible? Are these minerals? No. Of course, plastic and concrete are not minerals. But why aren't these substances considered minerals? These substances are not considered minerals because plastic and concrete are made by people. Although they contain minerals, these substances are not found in nature. And as we said in our definition, minerals occur naturally. That is, they develop through nature. Now, how about these substances or products? Why aren't they minerals? This piece of coal, this cotton shirt, or these crackers? Why aren't they minerals? Minerals cannot be made from living things. That's why a mineral is described as being inorganic. These products are made from living things. Even coal is the remains of organic bodies that lived millions of years ago. How about these substances? Why aren't they minerals? The gas that powers vehicles, oil used for heating systems, or the water that makes up so much of the Earth's surface. Ask yourself, why aren't these substances minerals? All minerals must be solid. That's why liquids and gases, like these examples, don't meet our definition. Another point is that minerals have definite chemical compositions. Some minerals are made up of atoms of a single element, like this piece of gold. Others, like this quartz sample, are compounds, that is, made up of two or more elements. In the case of quartz, the two elements are oxygen and silicon. The last characteristic in our definition is that minerals must have a definite structure, similar to the form of a crystal. In other words, the atoms in a mineral are arranged in an orderly pattern that is repeated over and over, like the structure in this building. Notice how the girders form a framework of support for the structure here. In a mineral like this piece of quartz, we can see the crystal pattern. Quartz always forms a six-sided crystal. Remember then, a mineral is a naturally occurring, inorganic compound with a definite composition and structure. We now have a definition for minerals. But with more than 2,000 different minerals on Earth, how can we identify specific minerals? Think for a moment. What suggestions do you have for identifying and naming minerals? To help clarify our thinking, look at the people around you. Each person is unique. What are several features that help describe you and your friends? In describing a person, you might have mentioned height, weight, facial features, and other characteristics. In a similar way, minerals have their own unique characteristics that set them apart from other minerals. Color is the first characteristic that most of us notice about minerals. Here, for instance, the green of the malachite, or with this mineral, the blue of the lapis lazuli. Although color seems a good way to identify minerals, don't be misled, because the color of some minerals, like this quartz, can change due to the presence of other substances known as impurities. For example, here we have quartz made purple by a small amount of iron. And here, quartz that's rose-colored from the inclusion of the element titanium. Also, some minerals are almost the same color, even though they're different. Can you tell the difference between this mineral and this one? This one is pyrite, known as fool's gold. And this one is real gold. Color can also change when a mineral is exposed to the air. Normally shiny silver, for example, becomes dull and tarnished from air exposure. Since a mineral's apparent color is not reliable, we need other ways to identify minerals. The streak test is often used by scientists to determine a mineral's true color. Like rubbing chalk on a blackboard, the streak test scratches a mineral's surface to reveal what's underneath. All you need is an ordinary wall tile. Then, rubbing a mineral against the unglazed tile, the mineral breaks apart. Using the streak test on gold, the gold leaves a gold streak, and pyrite, fool's gold, leaves only a black mark. And the mineral hematite, which may appear red, brown, or even silver, leaves a streak that's always reddish-brown. But some minerals, like this quartz, or gems like diamonds, are so hard they don't turn to powder and leave any streak. Because of this problem, scientists use a scale of hardness, like the one we see here, to identify and evaluate minerals. Developed by a German mineralogist named Friedrich Moe, the scale has become a standard for geologists. Moh's scale of hardness rates minerals on whether they can scratch other minerals or be scratched themselves. Everyday objects like a fingernail, copper penny, and steel file are shown for comparison. On this scale, 1 is very soft and 10 is very hard. What is the hardest mineral shown here? A diamond with a rating of 10 is the hardest mineral here. What is the softest? Talc with a rating of 1 is the softest mineral and can be easily scratched by a fingernail. Cleavage is another test for identifying minerals. Cleavage refers to a mineral's tendency to split along flat surfaces, as in the case of this mica, which comes apart easily, always splitting in the same direction. Thus, geologists describe mica as having one good cleavage, while other minerals like feldspar, which splits 2 ways, have 2 good cleavages. Some minerals split 3 or even 4 ways. When minerals don't break along cleavage surfaces, geologists say they have fracture and break unevenly, like this piece of quartz. For identifying minerals, then, there are several reliable tests, including the streak test, the scale of hardness, and the cleavage test.
Believe it or not, new rocks are being formed every single day. How they form can be as loud and as violent and as dangerous as an erupting volcano. Or it can be as soft and as calm and as peaceful as the slow dripping of water in an underground cave. The fact is that rocks are being formed, transformed, and reshaped continuously all over the world. As we speak, rocks are being transformed in the hot desert sun, on cool ocean shores, and along rivers and streams. Rocks are being reshaped in the highest mountains, thousands of feet in the air, and being formed thousands of feet below the surface of the Earth. Hi, I'm Max Orbit. Learning about rocks is way cool, and so is finding and collecting rocks. Do you find rocks fascinating? Would you like to go on a rock hunting mission to start your own collection? Well, you can do it, and become an official rock finder. But first, you'll need to know all about rocks, the tools you'll need to go exploring, and what to look for when you get there. I can show you. But first, let's start our exploration by answering a simple question. What is a rock? Rocks are found everywhere on Earth, and throughout history, people have been using rocks to build things. It's been going on for thousands and thousands of years. The Egyptians used large rocks to make the pyramids. Stonehenge in England is made of giant-sized rocks. The Great Wall of China is made of rocks. And the ancient Greeks made temples out of rocks. For centuries, different cultures throughout the world have carved rock to make statues, monuments, and other works of art. We still use rocks every single day. As a matter of fact, this building is made almost entirely of products made from rocks. Can you name them? Go ahead, give it a try. I'll wait. Time's up. What did you come up with? If you said steel, you're right. Steel comes from iron mined from the earth. How about concrete? Concrete comes from limestone. Now there's one more material that may be a little tricky. Did you guess it? Well, it's glass. Glass is made from sand. Steel, concrete, and glass. All materials that come from rocks. I guess you can say this is one rockin' building. I guess you can say it, but I wouldn't. Because of weathering and the actions of animals, plants, and people, rocks are always changing. One kind of rock changes into a different kind of rock. We call the changing of rocks the rock cycle. Let's begin with igneous rocks. Weathering breaks down igneous rocks into small particles. Sediments are formed and pressed together to become sedimentary rock. Some igneous rocks are buried deep inside the earth, where heat and pressure change the rocks to metamorphic rocks. Sedimentary and metamorphic rocks are also changed by weathering. Sedimentary and metamorphic rocks buried deep inside the earth can change to igneous rocks or to other metamorphic rocks because of heat and pressure. There are lots of things that can affect the cycles of changes in rocks and soil. Wind, temperature, water, ice, and glaciers all cause the changes. It's the reason that landscapes all over the world look so different. It's the reason some places are mountainous and other places are deserts. Why some places are great for growing crops in rich soil and other areas are rich in trees and woodlands. When you think about it, the rocks, minerals, and soil found in any one place on Earth can tell the story of that place. If rocks could talk, what kind of story would they tell? I found this rock in a river valley. What I liked about this rock is that it's very, very smooth. What kind of story would this rock tell? What? Well, perhaps it would say that over thousands and thousands of years, deep river waters flowed over it, carving out a deeper and deeper valley while smoothing its once rough edges. I found this rock in a glacier valley. What's this rock's story? Well, if this rock could talk, it would talk about the frigid temperatures and the incredible amount of pressure it endured under thousands of feet of ice. It would talk about the scratches on its surface as it was scraped and worn down over thousands of years and finally left to settle in a glacier valley. This is a rock I found on a trip to the islands of Hawaii. It's an igneous rock. If this rock could speak, It would tell of the incredible heat beneath the surface of the Earth and how one day it exploded up through a crack in the Earth and flew hundreds of feet in the air. When it landed, it became part of a flowing sea of burning magma. But as it slowed down and began to cool, it changed from a hot, burning liquid to a black, solid rock. This is a rock I found while hiking one of the desert plateaus in America's West. This rock would tell quite a different story. Perhaps it was once part of a tall, majestic rock mountain that overlooked the dry, barren desert. Over time, wind-blown sand slowly eroded pieces of the monument away, and finally, this rock fell to the ground where it sat for many, many years, baking in the hot desert sun.
Marquis, see if you could tell me what the difference is between this rock and that one.
That's not a rock, that's a mountain.
You're right. It is a mountain. But it's a mountain made of granite, which is a rock.
And this is a granite rock.
So I guess the difference is the size.
Exactly right. Even though this rock is much smaller, it has the exact same ingredients. It's possible that at one time this rock was part of a much larger rock like that mountain.
So nature can change the size of rocks?
That's right. Over the centuries, rocks are exposed to wind, rain, snow, ice, and other forces of nature. When water seeps into a crack in a rock and freezes, the ice expands, increasing the size of the crack. This process, repeated year after year, eventually breaks rocks into smaller pieces. Plants can also break a rock. A root may extend down into a crack. As the root grows, it can break the rock apart.
This process of big rocks being broken into little rocks by nature and weather is called weathering. Chemicals can also weather rocks.
When water and CO2 from the air mix, they form a weak acid. This acid dissolves limestone and sometimes forms caves in the rocks. While weathering breaks down the rocks, it is erosion that moves them. We've talked about how rivers and streams can move sediment into lakes or the ocean. There are other ways that rocks are moved. Waves at the ocean are so powerful, they are constantly eroding rocky cliffs. Winds can move tons of dirt during a dust or sandstorm, and glaciers are even more powerful. A valley glacier is like a river of ice found only in the highest snowy mountains. A valley glacier can be 1,000 feet thick, and even though glaciers move very slowly, they have the power to break off and drag a boulder the size of a house. The final stage of movement is called deposition. When wind and water finally calm, the rocks and the sediment settle to the bottom. They are deposited in different areas. We saw deposition in the formation of sedimentary rock.
Would you believe that I could change a sedimentary rock into an igneous rock?
Not really.
You're right. I can't. But nature can.
If you're an avid rock finder, you may someday uncover a fossil on one of your expeditions. So it's important that you know a little bit about fossils. Fossils are bones, teeth, and other remains of plants and animals that lived a long time ago. Fossils are buried underground. But how did they get there? Well, usually when we think of fossils, we think of dinosaurs. Now, no one has ever seen a real dinosaur because there aren't any more around. They're extinct. But we do know a lot about them because of fossils. There are different types of fossils that scientists have discovered. The first type of fossil is called a body fossil. How do body fossils form? Well, let's say a dinosaur died near a pond or a lake. Over the years, sand and mud piled up around the dead dinosaur. The soft body parts like skin, brain, and heart decayed. However, minerals from the ground seeped into the bones and teeth, and eventually the hard parts of the dinosaur body turned into rock. That's what a body fossil is. The next type of fossil you may uncover is a trace fossil. A trace fossil is formed when an impression is made in mud or dirt. The impression dries and becomes hard and eventually turns to stone. A trace fossil is made from any impressions like footprints, skin, or, in this example, the feathers of Archaeopteryx, a primitive bird. You're probably wondering, where do you find fossils? Well, to find fossils, you have to dig! Today, special scientists called paleontologists carefully dig up dinosaur fossils so they can study them. A paleontologist is a scientist who studies fossils. He's a special kind of rock finder that travels the world digging up fossils. It's long and painstaking work. Paleontologists and their helpers chip carefully away at rock and then brush away the dust, being careful not to crack and ruin the fossil. Once they find a fossil, they cover it with plaster to protect it. They pack the larger fossils in crates and send them back to a laboratory. There, the plaster is removed and the fossil is examined. Some fossils are put in displays in museums all over the world. It's fun to go out and hunt for fossils, but it's fun to make your own too. To make your own fossil, you're going to need some clay and a seashell. Here's what you do. First, flatten out the clay until it's nice and flat. Then, take your seashell and press the shell into the clay. You've just demonstrated in seconds what it took nature many, many years to do. Form a trace fossil. If you want to preserve your trace fossil, put the clay fossil in a place where it can dry overnight. Then take brown shoe polish and brush some of it over the imprint, and then spray it with acrylic spray. But ask an adult for help with that part. Now you can also make imprints of other things as well. An acorn, a leaf, or even your thumb. Now that's fun with fossils.
We know soil is the loose material that covers the earth. Soil is made of tiny bits of rock and small pieces of dead plants and animals. Some people call soil dirt.
Don't forget that soil has water and air in it too. I absorb air from the soil every day, so I know that there's air in the soil. And the water, well, there was too much water in the soil last week during those heavy rains. I had to get out of that mud. That's why you saw me on the sidewalk. Oh, and thanks again for watching your step when you walked by.
No problem. Let's go into the slime lab and see what other facts we can dig up on soil.
All terrestrial or land-covered surfaces of the earth can be described with three general categories: unfragmented rock, bare rock surfaces, and faces. Bare rock is a common part of many mountainous regions. Regolith, or blanket rock, is a layer of loose rock laying on the unfragmented rock below. Soil. Soil is a mixture of both inorganic or non-living particles derived from rock and an abundance of organic substances. These include plant and animal material, both living and dead, and many microscopic organisms. Soil rests on top of the blanket rock and is by far the most common land feature of the planet. Soil is sometimes called the skin of the earth. Here, in cross-section, we can see the zone of plant growth at the top. But we can also see that the plant roots extend downward in some environments, as much as 7 feet deep. If we look at a soil sample taken from this drill rig, we can see the top layer is a type of clay with some organic material. The middle layer is an inorganic mixture of gravel and sand. And the bottom layer is bedrock, made up of sedimentary rock.